Today, let's do some more examples on limits. And on this slide, we are going to focus on the ones with zero denominators. So let's take a look here. Zero denominators. In other words, we are going to work on some problems with division by zero. So let's make a note up here that it's going to be about division by zero. By zero. And I am talking about this kind of form. Non-zero value divided by zero. Let's call this non-zero value x. So x right here, non-zero, divided by zero. This form. As you can see here, the denominator is equal to 0, so we call it zero denominator. This one has to be 0. However, you have to keep in mind that the numerator in this form has to be non-zero. So what we have up here for x, the numerator has to be non-zero. Not equal to 0. This form is different from the one that we saw in the last lecture. In the last lecture, we saw this form, 0 divided by 0. Let's write it down. We saw this last time, 0 divided by 0. And at this point, we know that this form is indeterminate. Okay, this one is indeterminate, which means that we don't have any conclusion with it. Inconclusive. And as you can see here, one of these forms has the numerator that is non-zero, and the other has one that is 0. So they are not equivalent. So they are not the same, not equivalent. So make sure that you know the difference between them. And today we are going to focus on the one with the numerator that is not 0, x divided by 0. And the reason that I have to focus on this zero denominator form is that it's very easy to make a mistake out of them. And every year you guys did that. And let's see why. So let's start by looking at this example number 1 right here. So here we want to find the limit of this function, 1 over x minus 1. So this is the function that we need to work on. Fx equal to 1 over x minus 1, a fraction. And we want to find the limit of this function when x approaches 1. When x gets really, really close to 1, but not there. Okay, now we need to use an approach in order to find this limit value. And usually we start with the one that is easiest and simplest, and that is direct substitution. So let's do that. Try the one that is easiest, and that is d sub, direct sub. And for this approach, we are going to put in x equal to 1 right at that point. X equal to 1, and let's see what happens. Now 1 goes in, we have this 1 divided by x equal to 1 minus 1, and we have 1 divided by 0. And there you go, we have this form. Non-zero value as numerator divided by 0 denominator. And this is definitely the form that we want to focus today. 0 denominator. Okay. Let me highlight on this one. So this is the form. Now, at first glance, 1 divided by 0, you think that this should be equal to infinity. Because we have 1 divided by 0, it should be something really, really big. So many of you would expect this to be equal to infinity. Non-zero divided by 0 should be infinity. But the question is this true? I am not so sure, so let's check on that. Okay, so once again, it's all about finding the limit. So here, what's important is that we know the condition for the limit to exist. And I am going to call back what we learned from the last lecture, the conditions for the limit to exist at any point. We have 3 conditions. Okay, let's start with number 1. For a limit to exist at any point, it must have the right-hand limit at that point. First, have our limit. The second condition, number 2, it must have left-hand limit at that point. Have left-hand limit. And last condition, the right-hand limit and the left-hand limit must be equal. R must be equal to L. Okay, if you have these 3 conditions met, then the limit exists at that point. And we are going to check on these 3 conditions right here for this example. Okay, I'm going to start with this right-hand limit for this example that we have. So I'm going to start with this. Okay, right-hand limit, R limit. Okay, and it's going to be this limit of this same function, 1 over x minus 1. And we want to approach 1. X approach 1 from the right-hand side, which means that we are coming from the positive infinity. Coming from the positive infinity, and that's why we need to have this positive sign right here. We are going to check on this right-hand limit. And of course, we need to check on the left-hand limit too. Now, talking about left-hand limit. Once again, it's going to be similar. Limit of the same function when x approaches 1. But this time we are approaching from the left-hand side. Coming from the negative infinity, so that's why we need to have this minus sign right here. Okay, so x approaching 1 from different direction, how is that going to affect anything? Let's take a look here. So let's assume that we have this x-axis. Okay, x-axis, and we are interested at this point at x equal to 1. At this point, x equal to 1. Okay, this is the point that we are interested in. And let's check on the right-hand limit first. So we are moving from the positive infinity. Oh, by the way, let's have this right here. This is negative infinity and this is positive infinity. First, we approach from the positive infinity from the right-hand side. So we are going to go in this direction and get really, really close to 1, but not there, just before 1. Since we are approaching from positive infinity, it's going to stop at a value that is slightly larger than 1. So approaching in this direction, we are going to get this value, 1.00001, a little bit larger than 1, right? So let's use this number into in the right-hand limit expression. So this limit is going to be about the same as 1 over, now x right here is going to be slightly larger than 1. So let's use that 1.001. So this 1.000, okay, 01, just a little bit larger, and minus 1. Okay, let me fix that. Oh, I'm sorry. 1 right here. Okay, so what do we have here? It's going to be about the same as 1 divided by. So we have 1.0001 minus 1. It's going to be about the same as 0.00001. Something like that. Okay, and that is for the right-hand limit. Now let's check the left-hand limit. So this time around we are approaching from the left-hand side. So we are approaching from this direction, along this direction, and we are going to stop just before x equal to 1. So it's going to be a value that is slightly less than 1. So along this direction, you are going to approach this value, 0.99999, really, really close, but not there. So this is coming from the left-hand side, and let's use that for the left-hand limit. About the same as, Okay, so this time coming from the left we have this value 0.99999 minus 1, and we want to find the value of this. So let's find out. Okay, now let's take a look at this subtraction right here. This is 0.999, a little bit less than 1, which means that we have a subtraction with the front term less than the back term, which means that the result of this denominator has to be less than 1. Oh, sorry, less than 0. Has to be negative. Okay, so what we have right here, 1 over 0.999 minus 1, of course we have this minus 0.00001. Okay, that is the main difference. Up here we have the front term. For the subtraction, the front term is larger than the back term, and this results in the denominator that is greater than 0. For this one down here, for the left-hand limit, we have front term that is less than the back term, and that's why we have denominator that is less than 0. Okay, and let's check out why this is important. Okay, up here with the right-hand limit, we have this term, 1 over 0.001, and this is going to be about the same as positive infinity, 1 over a really small number, and that number is positive. Okay, what about this one? 1 divided by a really small number, but it's negative. So in terms of magnitude, it's going to be large, but in terms of sign, we still need to keep this minus sign right here, which means that this box down here for the left-hand limit is going to be about the same as minus infinity. And as you can see here, right-hand limit about the same as positive infinity. Large number that is positive. And down here, large number that is negative. They are definitely not equal. Not equal here, which means that this is a violation of condition number 3. They're not equal. So in terms of conclusion right here, we have seen that these two are not equal. So this is not true. It's not equal to infinity. And we can conclude for this example that for this one, because the right-hand limit and the left-hand limits are not equal, so the conclusion is limit does not exist. Or in other words, no limit. Okay? So, what about we try to look into this by using a graph so that we see what's going on, why one of them goes to infinity and the other goes to negative infinity, right? So let's check on that. I'm going to use the graph on the right-hand side. So let's take a look at this point that we are interested in. X approaches 1. So this is the point that we want to study. And let's put a line right here. Okay, let me fix on that. Okay, now we want to approach this point. From the right-hand side, we want to find the right-hand limit. So at this point, I want you to look at the function itself. The function itself is this 1 over x minus 1. Let's take a look at this. Let me highlight this. Now, let's think about this in your head. What happens if x is really large? For this box, if x is really large, then the denominator is going to be really large, right? So the function value is going to be really small. So we are going to start at somewhere around here. When x is large, the function is small, but it's still positive because we have this front term greater than back term. And now when x gets smaller, denominator gets smaller, and your function value starts to increase. So you are going to get something like this. Starts to increase, and it's going to go to positive infinity. Okay, and that's how you get the right-hand limit. So approaching from the right-hand side, it's going to go to, starting from really small, and it goes to really, really big and positive. So what you see right here is the right-hand limit. Limit of 1 over x minus 1, x approaches 1 from the positive side, equal to positive infinity. Gets really large and positive. Now let's see what happens if we approach this same point from the left-hand side. Now we are going to approach from the left-hand side. Okay, now let's take a look at this box again. Function value that we have right here. Let's imagine that x is really large and negative. Okay, this fx. If x is really large and negative, then the denominator is going to be really large too and negative. So the function value is going to be small but negative. So you are going to start somewhere around here. Small but negative. And now as x increases, right, so the denominator will get smaller. Okay, and once it gets smaller, the value, the magnitude of this function is going to get larger, but it stays negative. It gets larger but stays negative, so it's going to be something like that. And then it approaches minus infinity this way. Okay. Alright, so this, what we see right here is the left-hand limit. Okay, this is left-hand limit. Limit of 1 over x minus 1 when x approaches 1 from the left-hand side. This time it's large but it's negative. Minus infinity. And as you can see here, one of them points to this point really far away, positive infinity. But the left-hand side, it points to negative infinity. Definitely not the same. So this is a violation of condition 3. Right-hand limit is not equal to left-hand limit for this function at this particular point. Therefore, we may conclude that there is no general limit at this point. Therefore, no general, or you can say overall, limit at this point at x equal to 1 for this function in this example. And that is the answer. No limit here. Limit does not exist. As you can see from this illustration, the signs for the left-hand limit and the right-hand limit can be different. One of them can go to positive infinity, while the other can go to negative infinity. So this is something we need to watch out for. It can happen. And I just want to let you know that this kind of scenario or situation can happen with this form, 0 denominators. This form. So if you run into this form, 0 denom, you need to watch out for this kind of problem. Different signs of the right hand and left hand. And the only way to check on this is to put some work in. So let's make a note right here. When you run into this 0 denom, always check the signs. Okay, right here, always check signs. We are talking about positive and negative, okay? Sign of positive and negative of the denominator, of denom, for both left-hand limit and the right-hand limit. Okay, left and right. You need to compare them. If they come out to be the same signs, then you can conclude that it has a limit. But if they come out to be different signs, you have to say otherwise. And that is the idea. Okay? Always check when you run into 0 denom. And we are going to work on some more examples here. So let's take a look at this example number 2 down here. Okay. First of all, let's take a look at the function we have for this limit. So we have this fraction. Okay, 1 over x plus 3, and the whole terms right here, square. So we have this as our function for this second example. Okay, at this point, I want you to compare this function to the one we had in the example number 1. it's quite similar, except that this time around we have square right here. And this square right here is going to make a difference. We'll see why. Okay, now let's try to find the limit of this function. And we want to approach minus 3 to get really close, but not there. Alright, so as always, we start with the easiest and simplest approach, and that is the direct substitution. So let's do that. So let's try direct sub. D sub. And for this, we are going to put in x equal to minus 3 exactly. X equal to minus 3 is going to go in. So let's check on this expression over here. 1 over, inside the parenthesis, we have x equal to minus 3 plus 3 square. Okay, looking at this, we know that this is going to go to 0. So we have 1 over 0 square. Of course, we are going to have this 1 over 0. And as you can see here, this is a non-zero numerator divided by a 0 denominator. Of course, this is 0 denom form. And at this point, we know that we have to be careful when we have this 0 denom. And what we need to do here is to check the signs. Check signs of right and left hand limit. Okay, let's do that. Okay, it's because of this 0 right here. So let's start with the right hand limit. Let's do that over here. Start with the right hand limit. Let's put the notation in. Limit of the same function, 1 over x plus 3 square. X approaches minus 3. Coming from the right hand side, coming from the positive infinity, we have positive sign right here. Okay, now let's take a look at the value of x right here. We are approaching minus 3 but not there, and we are moving from the right hand side. So the value that we are going to use here is going to be a little bit larger than minus 3. Coming from the positive side, right, it has to be larger. So x right here is going to be around minus 2.999, lots of 9s. Okay, slightly larger than minus 3. Now we are going to put this number into our expression. Okay, let me fix this a little bit too big. Okay, minus 3. Okay, now this is going to be equal to 1 over, let's put that number in. X is about, oh, I should say that this is about not equal. Okay, so x equal to minus 2.999, go in. Okay, minus 2.999, lots of 9s, plus 3 square. So this is what we have here. Now let's take a look at the terms inside the parentheses. Minus 2.999 plus 3. So the result of this is going to be positive, right? Because minus 2.999 less than 3. So what we have right here inside the parentheses would be positive greater than 0. And with this, we can try to find the value. Okay, so the result from the addition here, 3 minus 2.999 is going to be 0.00001, really small. So in the end, it's going to be extremely small with this square right here. With this square right here. Becomes really small. 1 over, okay, 1 over 0.000, lots of zeros, 0, 1, and it's positive. This is important, positive right here, and it comes from this, positive. And as you can see here, what we have at this point is 1 divided by a really small number. And of course, this is going to become really big. So this is about the same as positive infinity. Alright, and that is the right-hand limit. We got the positive infinity. Now we are going to check on the left-hand limit. Okay, let's do that on the right-hand side. Okay, left-hand limit. Do the same thing. So here we have the limit of the function 1 over x plus 3 squared. This time we approach minus 3 from negative infinity, and that's why we have this minus sign coming from the left-hand side. Talking about the x value, the x value that we use here is going to be a little bit less than minus 3. A little bit less than minus 3. I would say that it's going to be about minus 3.00. Lots of zeros and ends with 1. And this number is, just a little bit smaller than minus 3. And let's put this number in. So here we have 1 over, not equal. Okay, estimation. 1 divided by. Okay, this number goes in minus 3.001 plus 3. And we have square right here. So this is what we have, and let's check the terms inside the parentheses. Minus 3 something plus 3 something. The result of this is going to be negative, right? So what we have right here is negative. This doesn't sound good. It used to be positive. Now it becomes negative. However, we have this square right here. The square right here is going to make this negative value inside the parentheses become positive anyway. So with this, it's going to be positive. Okay, so in the end, we are going to get this really small number, right? Difference between 3.0001 plus 3 is going to be this 0.0001, and it's positive because of this square right here. So we have positive sign. And with this, 1 divided by a really small number that is positive. We know that this is about the same as positive infinity, and that is the value for the left-hand limit. Okay, and as you can see here, right-hand positive infinity, left-hand positive infinity, same sign, same value. So we may conclude that the limit for this example exists and it's equal to positive infinity. So for this, we can conclude after checking equal to positive infinity. Right-hand limit equal to left-hand limit equal to this positive infinity. Alright, now as you can see, the result of this example is different from the first one. The first one doesn't have a limit, but this one does. And the reason is because of this square right here. It's the game changer. It changes this negative value, negative denominator to become positive. So most of the time, if you see square right here, you sort of know that this thing is going to be positive. So you don't need to worry about the different signs. Alright, so watch out for this square. You have this, it stays positive. Okay, this stays positive. Okay, let's check on one more example here. Okay, this one down here also has the square, but it's not outside the parentheses, it's just for the x right here. Let's see what's gonna happen here. Okay, once again, let's take a look at the function we have. We have this as our function, a fraction of x minus 3 divided by x squared minus 4. And we want to find the limit of this when x approaches 2. Once again, we try direct sub as our first step. D sub. Okay, because it may work. And for this, x is going to be equal to 2 exactly. Now 2 goes in. 2 minus 3 divided by 2 squared minus 4. So we have minus 1 divided by 0. Okay, we have this form again. Non-zero value divided by a 0. Definitely, this is 0 denom. 0 denom again. And this means that we need to check on the right hand limit and the left hand limit. What about we just check the denominator? I'm going to check the signs of this. Okay, I'm going to start with the right hand side. Right hand side, when x approaches 2 from the positive side, this means that x is going to be around 2.000 something, 01, a little bit larger than 2. And now I'm going to check the denom. So denom, we have this x squared minus 4. We are going to check on this. So what we have right here is we have 2.0001, okay, square minus 4. And from this you can see that the front term is larger than 2, which means that if you square this, it's going to be larger than 4, which means that this whole term right here is going to be positive. That's what we have for the right hand limit. Now let's check on the left hand limit. Okay, for this one, left hand limit, and this is x approaching 2 again, but we are approaching from the left hand side, so we have minus over here. Talking about the value, x is going to be a little bit less than 2. So I would say x about equal to 1.999 all the way. Okay, and this number is going to go in. So let's check on the denominator here. Once again, x squared minus 4. And what do we have here? Okay, so we have 1.99999 square minus 4. As you can see here, this number is less than 2, so the square of this is going to be less than 4. This thing less than 4, which means that the subtraction in the end would come out to be negative. Okay, so we have this. At the end it becomes negative because the front term is less than the back term. As you can see, this one negative, and it's different. Right hand positive denominator, left hand negative denominator. So we may conclude that for this example, the limit right and left would have different signs. Therefore no limit here. Okay, so even though we have square right here at the denominator, just like we did with the second example, but this time it's just one term. This is different, so you need to be careful on this. I don't want you to see square and conclude right away that it's going to be positive. It's going to be positive only if the square takes the whole terms, takes the whole denominator. This down here is different. Okay, and these are the examples for the zero denominators. Now let's move on to some more advanced example. This is going to be challenging to you. In this first challenging example, we want to find the limit of a function right here. So let us first take a look at the function that we have. So we have sine theta divided by theta as our function. As you can see, we only have one variable here, and that is theta. So we are going to call this one function f with theta as our input, or the variable. And we want to find the limit of this function when theta approaches 0. That is our condition. Theta gets really close to 0. Before anything, let's take a look at this function that we have right here. Sine theta divided by theta. This looks simple, right? At first glance, this shouldn't be that bad. Just a fraction of one term over another term. Finding the limit shouldn't be that difficult, you may think. It turns out that in order to find the limit of this function at this point, it's surprisingly complicated, and we need to rely on many tricks, and you are going to see them very soon. So let's take a look here. So we want to find the value of this limit, and that is our goal. We want to find this. And as always, we are going to start with the easiest approach. Okay, direct sub. Of course, you can expect direct sub to not work here because this is challenging, right? It's supposed to be hard. And direct sub is not supposed to give you anything, but it's a guarantee that, hey, we try direct sub and it doesn't work. That's why we need to rely on some more advanced technique. So let's try anyway, d sub. And for this, theta is going to be equal to 0 exactly. Okay, let me save some space over here. Okay, so what do we have here? We have sine theta, theta equal to 0. So we have sine 0 divided by 0, theta equal to 0. So for this, sine 0 is equal to 0. So we have 0 over here divided by 0. Okay, so we have this form. Let me ask you, is this form indeterminate or zero denom? We just learned about zero denominator, right? Which one is it? As you can see here, for this one, the numerator is 0. So this is not zero denom. So this is indeterminate. Indeterminate. It means that we can't tell anything about this. No conclusions. Inconclusive. It means that we need to find other ways. This means that try something else. Okay, let's try right here. Let's try something else. Try other techniques. What about we try this factorization? We have tried this before. Factorization, it may work. Let's try this first. Okay, factorization, we need factors. But looking at this, we have only one term for the numerator, just sine theta, and just one term down here. I don't think we can factor anything. There is nothing to factorize. So I don't think factorization is going to work in this case. Okay. Now, what about conjugation? Okay, this is something we know. Conjugation. In order to use conjugation, we must have some patterns. And we are talking about a minus b or a plus b. So we need this a minus b or a plus b to use conjugation. And as you can see, looking at this, no such thing. Just one term for both numerator and denominator. So conjugation out of the question. It's not going to work. What about we try trigonometry properties? Okay, trig properties. You know, we know all these properties. Maybe we can change some terms. We can transform, and we can get maybe some simple terms, maybe some cancellation to make it work. Okay, let's try trig properties. Okay, let's take a look here. Is there anything we can apply to sine theta to change it to something else that is simpler? I don't think so. This is as simple as it can be. It's sine theta. Same thing here with the theta. So I don't think we can use any properties here. So trig properties are going to fail too. I think we are running out of ideas right now. Factorization, conjugation, trig properties. What about we try something from long time ago? Something we learned in middle school, or maybe for some of you, you learned it in elementary school. We are going to try geometry. Okay, number 4. Okay, number 4 right here. We are going to try some old technique, geometry. I wouldn't say technique, old topics that we learned from long time ago. Geometry. Okay. What is it about? Geometry. It's about shapes, lines, shapes, lines. We are talking about the areas of shapes, circumferences of shapes, something like that. Area. Circumferences. Okay, we are going to try this one, and let me tell you, this is going to save us here. This is going to be the hero for this problem that we have. So number 4. This one is going to be the technique we need, geometry. So I'm going to start with the unit circle on the right hand side. So we have this circle right here. Oh, by the way, I think you need to put y-axis right here and x-axis down here. And keep in mind that what you see right here is a unit circle. Unit circle. What this means is that it's a circle of radius 1. Unit circle, unit, r equal to 1. So this is length of 1, and okay, what about this? Right here is 1, minus 1, 1 right here, 1 right here, and minus 1 right here. And we are going to make use of this unit circle to solve this limit. Okay. This might sound surprising, but it will work. Let's take a look here. So first of all, I'm going to do something with this unit circle. I'm going to create a slice inside it. So I'm going to create this slice. Okay, let's call this slice. What about the angle inside this slice is theta, like a slice of pizza right here. So we are going to play with this slice right here. Now, the next thing I'm going to study on this slice is this side right here, this line. Coming from the edge of this circle, it's going to go down, straight down to the x-axis. So we are going to focus on this line right here. This is going to make 90 degrees with the x-axis. And let's assume that the length of this line is a, small a. Okay, and now we have another line to focus on. Okay, this one, first line. Another one is the curve on the edge of this unit circle. And just on this slice right here with the angle of theta. Okay, this green curve. Let's assume that the length of this green curve is b. And now we want to compare a and b. As you can see from the shape of this, b is the outside of is on the edge and a is inside. Of course, b has to be longer than a. Okay, so we have established this relation between them. B is outside, so b has to be longer than a. So I'm going to put this right here. Small b is going to be longer than a, but just in case, I'm going to put equal sign right here. Okay, what about I put it in black? B greater than or equal to a. So this is the main inequality that we are going to use at first step. Now we are going to do something with a and b here. Okay, now for a, I'm going to use trigonometry. Let's take a look here. I want to find this sine theta. What is it equal to? So sine theta is equal to the ratio of the side opposite of the angle divided by the hypotenuse. So it's going to be this side right here, opposite of the angle, opposite side divided by the hypotenuse. Hypotenuse here is the radius of the circle, so the length would be 1. So sine theta would be equal to a over 1. A over 1. And with this, we know right away that we have this relation between them. A equal to sine theta. Let's keep this. A equal to sine theta. We are going to use this later. Now, let's do something with b. And for this b right here, we are going to use the formula we learned from a long time ago, maybe 10 years ago. For me, for you, but for me, like maybe 30 years ago, I don't know. So let's take a look here. For b, we are going to use this formula. I am sure that you know about this formula. Formula of the circumference of a circle. Circumference equal to 2 pi r. But we are not going to use this formula directly. We are going to use this as our reasonings. So the reasonings would go here, right here. So at this point, we know that the formula that we need to use is 2 pi r, and we are going to get the the length of the curve on the edge of the whole circle. So let's write that down. Angle of 2 pi. Angle of 2 pi means the whole circle. Okay? Leads to curve on edge. Curve on edge with length. Okay. If we are talking about the whole circle, the curve on the edge of the circle would have the length of course, it's going to be this formula, 2 pi r. So we have this 2 pi r. Now, what about we don't want to study the whole circle? We just want to study just one slice right here. So we are going to change this to angle of. Now, not the whole circle. We are interested in only a piece, a slice of theta. And this is going to lead to the curve. What about I do this? The curve on the edge with the length. And now we can do the direct comparison, the ratio. It's going to be equal to theta times 2 pi r divided by 2 pi. And this cancel. So in the end, we have this theta r as the length of the curve on the edge with the angle of theta only. This might sound confusing at first, but let's take a look here. Whole circle, 2 pi, would give the circumference of 2 pi r. But if we want to take just one piece out, just theta, it's going to be this. And as you can see here, we are looking at a unit circle of radius equal to 1. So in this case, we are going to have radius equal to 1. R equal to 1, which means that in this example that we have illustration, we are going to have this curve on the edge with the length of theta. This theta right here is going to be the curve on the length of the curve on the edge. And that's going to be equal to this small b right here. The length of the curve on the edge with the angle of theta only. Okay, so this b right here, we know it's going to be equal to theta in this case. And it came from this one right here. Equal to small b. Now we have associated a with theta right here, and b with theta right here, and we are going to use them in our inequalities right here. We are going to work on this. So a equal to sine theta. So we have this a equal to sine theta less than or equal to b, and here b equal to theta. So we have b equal to theta. Now I am going to divide both sides with the theta. So I have sine theta divided by theta less than or equal to 1. And we are going to keep this for now. We know that sine theta divided by theta is always less than or equal to 1. And keep in mind that this is the function that we had in the beginning, function of theta. Let's keep it. And we are going to call this condition number 1. Now we are going to move on to another step, and in this for this time we are going to use geometry again, but this time around we are going to use areas. Okay, on the same slides, but I don't want to erase what I just drew already. I'm going to put it on the other side of the circle. Let's assume that it's the same thing. So let's do this. I'm going to have the same slides on the other side. What about this? Straight down. Okay, same angle. And I'm going to use geometry on this slides again. And this time I'm going to study the area of shapes. What about I start with the area of this slice of pizza, this piece right here. Let's call it big A. Okay, so this piece has the area of big A. And now I want to compare this region with another one. And the next one would be this one right here, the extended version of the slice. It's going to be something like this. Okay, and go up here and come straight down to the x-axis. And this is going to make 90-degree right angle. So we are talking about this extended piece right here. Okay, I'm going to try to highlight this side right here. Okay, so this, let me fix on this. I don't think it looks straight. So what about that? Okay, this looks a little bit better. Okay, so we have this extended piece right here. And we are talking about the area of the whole triangle. This big one. And we are going to call this area B. Big B. Big B and small a. Now let's compare big B and small a. Not small a, the a inside. As you can see here, the area of the extended version is big B, and it has to be bigger than the area of the slides inside. So what we know from this for sure is that the area of the extended piece, big B, is going to be larger than the area of the slice of the pizza, area of big A. So we have this inequality, another one. And we are going to do something with this again. We are going to change big A and big B into theta and find something out about it. So why don't we start with big B? Okay, let's start with this one. Big B outside. We want to find the area of this piece. Okay, so let's take a look here. Let's assume that the side over here, the height of this triangle is small l. And for the base, you know the base. The base is the radius of the circle is going to be 1. So one thing we know for sure is that the area of this big B is going to be 1/2 times base times the height. So let's work on that. Big B right here is equal to 1/2 times the base, which is radius of 1, times the height. But not just that. We are going to apply some trigonometry here. And let's use tan theta. Let's find out about that. Tan theta is going to be equal to the ratio between the opposite side of the angle to the close side of the angle. The opposite side would be the L. Over the close side is the 1. So tan theta, at this point we know it's going to be equal to L over 1. So it means that L is going to be equal to tan theta. So here we know that this L right here is equal to tan theta, which means that B is equal to tan theta over 2. Alright, that's what we know right now. Tan theta over 2. What about I keep it over here? Tan theta equal to tan theta equal to L over 1. Opposite side over close side. Alright, now we have B in terms of theta already. Now we have to find that kind of relationship with the big A. And once again, we are going to rely on the formula we learned from long time ago, and that is the area of a circle. Formula. Area of circle. Okay. Circle equal to, as you know, pi r squared. And we are going to use this as our reasoning again. Okay, doing the same as what we did before. So we have angle of 2 pi would give us the area of the circle. Area of the piece equal to pi r squared. Pi r squared. Let's take a look at this really quickly. We are talking about angle of 2 pi, the whole circle. Then the area of the piece, so we are talking about the whole circle. It's going to be pi r squared. But what if we are interested in just one slice? Angle of theta, one slice, it's going to correspond to the area of piece equal to, now we do the direct comparison, the ratio. So we have this theta times, let's use red, theta times pi r squared divided by 2 pi. So here we are going to cancel pi, and we have this equal to, but this is equal to, okay, 0 r squared. Okay, 0 r squared over 2. And for this example that we are working with, we know that radius is equal to 1. So r right here is going to become 1. So in the end, this is going to be equal to theta over 2. This is going to be the area of the slice of pizza with the angle of theta. This is the area, big A. Okay? So from this we know that area of A is equal to this theta over 2. Now we are going to make use of this. A equal to theta over 2 and B equal to tan theta over 2 over here on the left hand side. So let's take a look here. So A is equal to theta over 2, less than or equal to B, which is equal to tan theta over 2. Now I'm going to cancel this with this, and tan theta over here, I am going to express this as, okay, theta less than or equal to sine theta over cosine theta. And now I'm going to move things around. Move cosine theta to the other side and move theta down under sine theta. I'm going to get this. Sine theta divided by theta is going to be greater than or equal to cosine theta. Okay, and there you go. We have this second inequality to use later, number 2. Keep in mind that the right hand side of this inequality is sine theta over theta. Let me fix that. And this sine theta over theta right here is function of theta that we had in the beginning. So this one right here, okay, my pen is not working. Let me fix on that. Okay, f of theta. Now we are going to combine 1 and 2 together. Okay, let's work on that. Combined 1 and 2. Let's see what happens. So so we have sine theta over theta in the middle. Sine theta over theta in the middle. And we know from, okay, condition number 2. Let's start with number 1 right here. Sine theta over theta must be less than 1. So let's put it right here. Must be less than or equal to 1. And from the condition number 2 right here, on the bottom left, sine theta over theta has to be greater than or equal to cosine theta. So let's do that over here. This, we have cosine theta. Now, what we are going to do next is to apply limits to all of them. Okay, apply limit of this cosine theta when theta approaches 0. Same thing with this. Limit of this sine theta over theta when theta approaches 0. And same thing here. Limit of 1 when theta approaches 0. Now we need to find out about all of them. Let's start with this one. Limit of 1 when theta approaches 0. We don't have theta right here, so it doesn't really matter, so 1 stays the same. Okay, so 1 stays the same. Now we are going to keep this. This is what we want to know in the beginning. So let's highlight this one. This is going to be limit of sine theta over theta when theta approaches 0. This is what we want to know right here. Okay, now on the left hand side, okay, limit of cosine theta when theta approaches 0. So we are going to try the direct sub, theta equal to 0. And cosine 0 over here is going to be equal to 1. Okay, let's put this. Cosine of 0, and that's equal to 1. So we got to here, last line. So from this, we know that limit of sine theta divided by theta when theta approaches 0 is less than or equal to 1, and also greater than or equal to 1. What does this tell us? This is the value that we want to know. It's in between 1 and 1. Of course, this must be equal to 1. Alright, the technique that we just did, besides the geometry, this is called squeeze or sandwich technique. So what do you see right here? Okay, squeeze, or you can call it sandwich technique, because we can't find the value of this limit by itself, so we can squeeze it in from the left and the right, and here we have arrived at the final answer for this limit value, and that's equal to 1. Now let's move to the next challenging example. For the second challenging example, we want to find the limit of a function again. So let's take a look at the function that we have. So here, this is the function 1 minus cosine theta divided by theta times theta. So this is a function with one variable, and that is theta. We want to find the limit of this when theta approaches 0. Once again, try the direct sub for the peace of mind. Okay, let's take a look here. So our goal to find out about this, and let's try this. At least we know that the simplest approach doesn't work. So we try d sub, and this is when theta equal to 0 exactly. So let's see what happens. Equal to 1 minus cosine 0 divided by 0 times sine 0. This is equal to 1 minus cosine 0 equal to 1, sine 0 equal to 0. So we have 1 minus 1 divided by 0 times 0, and that is equal to 0 divided by 0. Once again, we have this indeterminate form. Okay, this one indeterminate. So we can't tell anything about this. No conclusion. So we have to try other ways. Try something else. Okay, factorization maybe, but I see something here. I see a pattern of a minus b. So I see this, 1 minus cosine. What about I try conjugation? Okay, from my guess, I'm going to try conjugation. Okay, let's do that down here. So limit of this, okay, we have 1 minus cosine theta divided by theta times sine theta when theta approaches 0. And a right here is 1 and b is cosine theta, a minus b. So I'm going to, oh, by the way, when you have a minus b, you want to multiply the conjugation in a plus b divided by a plus b. So I want to multiply a, which is 1, plus b plus cosine theta, divided by a plus b, 1 plus cosine theta. And let's see what's going to happen. So here is equal to, okay, what we have right here, a minus b times a plus b divided by a plus b. Okay, what we have right here is a squared minus b squared. So I'm going to get this, okay, once again I have the limit. Theta approaches 0. And now a squared minus b squared. A is 1 square minus b cosine theta square. Oh, by the way, I need to let you know that cosine theta whole term square is the same as cosine theta square. Same meaning, alright? Just in case some of you don't know about this. Now, divide this by, okay, what we have here is this whole term. Theta times sine theta times 1 plus cosine theta. Theta times, lots of terms here, sine theta times 1 plus cosine theta. Okay, so what's going to happen next? So here I have this 1 square is equal to 1, so I can take it out. So let's take a look at this. 1 minus cosine square. I think I can use the trigonometry property of this. Sine theta square plus cosine theta square equal to 1, which means that 1 minus cosine theta square must be equal to sine theta square. 1 minus cosine theta square equal to sine theta square. So this term right here should be equal to sine theta square. And I'm going to put this in instead of that two terms. So let's take a look here. Limit stays the same. Theta approaches 0. So numerator, we have sine theta square instead, divided by these whole terms. Theta times sine theta times 1 plus cosine theta. Alright, now at least we can cancel one of these, two of these terms. This one right here and the square right here. And at this point it's going to be equal to limit of theta goes to 0. And this is sine theta divided by theta times 1 plus cosine theta. So the form is different now. What about we try direct sub? Okay, now we want to try d sub, which means that we are going to put in theta equal to 0. So that's going to be equal to, okay, sine, okay, we are looking at this. It's going to be equal to sine of 0 divided by 0 times 1 plus cosine 0. So what is this equal to? Sine of 0 is 0. We have 0. And down here we have 0 times, well, cosine 0 here is 1, and the inside becomes 2, but it times with 0. So we have 0 times 2. So in the end, we still have this 0 divided by 0. Well, we got to this point again. 0 divided by 0. We know it's indeterminate, which means that at the current state, this is not enough to give any answer. Indeterminate, which means that we need to work some more. We need to work on this a little bit more. This is not enough to find the limit value. So looking at this, let's write it again down here. So we have the limit of sine theta divided by theta times 1 plus cosine theta. That's what we have right now at the current state. Okay, let me change that to sine theta. When theta approaches 0, And we know this is indeterminate if we use direct sub. But looking at this, I noticed something. I noticed something familiar, which is sine theta divided by theta, the example that we just did. I noticed this. Okay, why don't I group them together? So let's do that. It's going to be equal to limit of theta approaches 0, and I group the terms that I like together right here. The fraction of sine theta divided by theta times 1 over 1 plus cosine theta. If you multiply them back, it's going to be, well, equal. So it's the same thing, right? Now, what I want to do next is to put parentheses right here and right here. And at this point, we can distribute the limit to each one of them. Limit can be distributed to this first term and this second term. This concept can be applied to many operations like addition, subtraction, multiplication, and division. So let's write down right here. Limit distribution. Okay, we can do this. If you have limit when x approaches a of, well, two functions, first function and second function, and you are allowed to have some operations between them. Okay, like plus, minus, multiply, division. So if you have this, you can distribute limit into each one of them separately. Limit to this and limit to that. So in the end, you are going to get this equal to limit of the first term, x approaches a of fx, and you still keep the operations you have, either plus, minus, multiply, or division of the limit of the second term, gx, when x approaches a. Keep in mind that if you have this division right here, for this one, limit of gx when x approaches to a must not be equal to 0. Otherwise, you are going to get a 0 denominator. That's going to be a problem. So this one around that we have is multiply. So we can, distribute the limit to each one of them. So here I'm going to get this instead. Limit of the first subfunction. Okay, let's call this one f theta, and this one is g theta. So the first subfunction is going to be sine theta divided by theta, and we have theta approaches 0. Okay, now we need to multiply, keep the operation of the limit of the second subfunction. And second subfunction is 1 over 1 plus cosine theta when theta approaches 0. And from this one, we did that in the last example. We know that this is equal to, okay, this one this one right here is equal to 1. We did that. Okay, I'm still fighting with my pen right here. Equal to 1. Okay, now we need to work on this one. And for this one, I'm going to use direct sub. We need to apply theta equal to 0 into this one right here. So let's try that. Equal to 1 over 1 plus cosine 0. So what we have right here is 1 over cosine 0. This is equal to 1. So this is equal to 2, 1 over 2, for the limit of the second subfunction. So let's take a look here. This one, first limit from the last example, this is equal to 1. This one equal to 1. And for the second one, second limit right here, we just found it to be 1 over 2. So in the end, we multiply them together. We got the answer for this example to be equal to 1 over 2. And that is the final answer for this second challenging example.